Hey there, and welcome. Have you ever looked at the rocks under your feet and just wondered what story they're trying to tell? Well, today we're going to learn the basic language of structural geology to read those exact stories. And trust me, by the end of this, you're going to see the entire landscape in a completely new and exciting way. Have you ever been driving and seen a huge mountain range or even just a slice of rock on the side of the highway and thought, how in the world did that get there? Well, the answer to how these incredible structures form, it all starts with learning a pretty simple new language, the language of the Earth itself. All right, let's start at square one. Picture this. Millions of years ago, you've got sediment settling at the bottom of an ancient ocean. It's going to form a perfectly flat, horizontal layer. Like a single page in a big book, or a fresh, beautiful layer on a cake. But here's the thing. The Earth doesn't just sit still. It's an incredibly powerful, dynamic place. Over millions and millions of years, these immense forces are constantly pushing, pulling, and twisting these layers. And that twisting and turning, that deformation, is what creates all the cool structures we're about to explore. So, to describe exactly how these layers are sitting in the ground, geologists have a word for it: attitude. And no, it's not about whether the rock is happy or sad. It's just a precise measurement of its position and its tilt in 3D space. This is like word number one in our new language. Okay, so attitude is really made up of two key parts. The first one is called strike. And check out this analogy. It's a great one. Imagine you take a book and you tilt it into a tub of water. See that line the water makes right across the cover? That's the strike line. In geology, it's simply the compass direction of that line, where a tilted rock layer would meet a perfectly flat surface. All right, the second piece of the attitude puzzle is dip. So let's go back to our book in the water. The dip is just how steep that tilt is. Is it barely in the water, like a gentle 10 degrees? Or is it super steep, almost vertical, at 80 degrees? Now here's the really important part. The direction of the dip is always at a 90-degree right angle to the strike line. Put strike and dip together, and boom, you've got the complete 3D attitude of that rock layer. Okay, so we've got tilting down. We know rocks can be tilted. But what happens when you take those layers and you start to squeeze them from the sides? Well, they don't always break. A lot of the time, they just bend. Think about it like this. If you put your hands on both ends of a rug and you push them together, what happens? Buckles up, right? It gets all wrinkly. Well, believe it or not, the exact same thing happens to gigantic layers of rock over millions and millions of years. This squeezing force is called compression, and it causes the rock to create some of the most beautiful structures you'll ever see. And that bend, that beautiful curve in the rock, is what we call a fold. It's what happens when rocks are under so much pressure that they don't fracture, they just bend. They become ductile. And they create these amazing wave-like patterns you can see in the rock record. Okay, so let's dissect this fold. Everyone has three basic parts you need to know. First up, the hinge line. That's the tightest part of the curve, right at the very crest of that wave. Then you have the limbs. Those are just the flatter sides on either side of that hinge. And finally, see that imaginary flat surface that cuts the fold right down the middle? That's the axial plane. It's just a way for us to describe the fold's overall shape. This leads us to the two big players in the fold world, anticlines and synclines. An anticline is an upfold, and it literally looks like a capital A. Super easy to remember, right? A for anticline. In an anticline, the oldest rocks get pushed up right into the center. The opposite is a syncline. That's a downfold, kind of shaped like a U or even a smile. And you guessed it, in a syncline, the youngest rocks are the ones you'll find in the middle. Okay, so rocks can bend. But what happens when the pressure is just too much? Or if the rocks are too brittle and they can't just fold anymore? What happens when they just snap? That's right, they break. And that break is what we call a fault. Now, the key word here is movement. A fault isn't just a crack in the rock. It's a fracture where the two sides have actually moved and shifted past one another. And that movement, that's what causes earthquakes and builds entire mountain ranges. So to talk about how the rocks move on a fault, we need two more terms, the hanging wall and the footwall. And there's a super cool old school way to remember this from back in the mining days. Imagine you're a miner in a tunnel. The block of rock above the fault is where you could hang your lantern. That's the hanging wall. The block below the fault is where your feet are. That's the footwall. Simple as that. So how these blocks move tells us exactly what kind of fault we're looking at. There are three main types. First, you have a normal fault. This is when the Earth's crust is being pulled apart. That's tension. The hanging wall slides down. Next, a reverse fault. This happens when the crust is being squeezed together. That's compression. The hanging wall gets pushed up. And finally, when the blocks just slide horizontally past each other, like cars on a two-lane road, we call that a strike-slip fault. Okay, so attitude folds faults. We've covered a lot. But why does any of this actually matter in the real world? I mean, who cares? Well, you should, because understanding this stuff is actually fundamental to our modern lives. For starters, it helps us find things we need. Oil and natural gas, they get trapped in these fold structures. Valuable minerals, they often form along fault lines. It's also absolutely critical for building things safely. I mean, you definitely don't want to build a dam or a nuclear power plant on an active fault. It also allows us to understand and prepare for earthquakes. And maybe coolest of all, it lets us be geological detectives, piecing together the Earth's incredible billion-year history. So, the next time you're out and about, maybe on a road trip or just hiking, really look at the rocks around you. Look at the hills. You now have the basic vocabulary to start reading their stories. You can ask yourself, what forces shaped this place? Now that you know the language, what incredible stories are you going to see written in the landscape?